Assalamualaikum and good day. We continue again in 8086. Okay, now we are still trying to understand architecture of the 8086. Okay, okay. There must be some permanent. What we mean by permanent is that we cannot write. Okay, we is already being write before, so we cannot write. We only can read it. A permanent non-volatile memory to hold the program telling the CPU what to do when the power is turned on. Okay. As you know that when you turn on your PC, actually, it goes to the BIOS. BIOS is a ROM, which is a non-volatile. Okay. This collection of program is referred to as BIOS. BIOS, what we mean by BIOS? BIOS is stand for the basic input-output system. Okay, it contains program to test the RAM. Okay, the RAM uh, and also other component that connected to the CPU, the I/O, the hard disk. Okay, these are all done in BIOS. It also contains programs that allow Windows to communicate with a peripheral device. Also in BIOS. The BIOS test devices connected to the PC when the computer is turned on and to report any errors. Okay, if there were any error, then you can check in BIOS. Okay, now we look at stack. What we mean by stack? Why is it necessary to have a stack? Why we need a stack? I think you have studied in 8051. Okay. The stack is a section of read and write, so it must be in the RAM. It needs to be read and it also can write. Okay, used by the CPU to store information temporarily. Okay, why we need to store information temporarily? Okay, the CPU need to storage area since there are only a limited number of registers. You know that sometimes when you have a program which require a number of temporary data to be stored, okay, then you need to put it in stack. You don't have enough register to put temporary data. Okay, there must be some place for the CPU to store information safely and temporarily. It is what we need to have a stack. The main disadvantage of the stack is the access time. Since the stack is the RAM, you use RAM, and you know if you compare to register, it is take longer time to be accessed, okay, compared to the register. And we know also that there will be some processor which have a huge number of register. We call as a um, cache. Cache. Cache is uh, one kind of temporary to hold the data, which is much faster than RAM. Okay. If you if you require a more powerful computer, then you need to have you use to CPU which have a large number of cache. Okay, how you going to access the stack? Okay, the stack is a section of the RAM. It should be in the RAM since you can read it and write onto it. So there must be register inside the CPU to point to it. Okay, there are two two register. The first one is the stack segment register, and the other one is the stack pointer register. Okay, by combine these two register, then you can access it physical address of the stack. Okay, this register must be loaded before any instruction accessing the stack are used. Okay, you have to define it in the beginning of the program. You have to define it. Where is the stack? Every register inside the 8086 can be stored into a stack. Okay, if you want to store temporary data on particular register, okay, you can put it onto the stack and brought back into the CPU from the stack memory. Set segment register which are not allowed, and the stack pointer also are not allowed. Any other register you can put it onto the stack. Storing a CPU register in the stack is called a push. Push is the instruction. I think in the 8051 also you can use push to load the register onto the stack. Okay, and to call it back, okay, and put the content of the memory onto the register is called pop. You use pop instruction. Okay, in the 8086 stack pointer register point at the current memory location used as the top of the stack. Okay. Stack pointer. Okay, we have stack segment and stack pointer register. As the data is pushed onto the stack is decremented. Okay, it is decremented. Okay, it is different from the execution of the stack. When you push one data and then it will be decremented. When as the data is popped off, okay, you want to take the data from the stack into the CPU, it is going to be incremented. What is going to be decremented or incremented is the stack pointer register. When an instruction push or pops a general purpose register, it must be entire 16-bit register. Okay, you cannot uh, only put only 8-bit register, for example, push AL or push AH. You must write a code push AX. AX is a 16-bit register where there will be no instruction such as push AL or push AH. Okay, the stack pointer is decremented after the push instruction is to make sure that the stack is growing down from the upper addresses to a lower addresses. The opposite of the instruction pointer. Instruction pointer, as I mentioned earlier, it is a execution of the code. When you point to the code, okay, after you execute, after you use, then it will increment. To ensure the code section and the stack section of the program never write over each other, so they are located at the opposite end of the RAM set side for the program. You have to put it in end side, opposite end inside the RAM, because they are growing toward each other, but must not meet. If they meet, then the program will crash. So normally when you that is the other error, syntax error uh, came across when you are coding a program where the stack is not correct. The one that you store temporarily is not correct. How is it come to this situation? Is because it the program and the stack are meet each other. Okay, pushing uh, the register onto the stack. Okay, as each push is executed, push is the instruction to put the register onto the stack. The register content are saved onto the stack, and the stack pointer is decremented by 2. Okay, since each of the location only 8 bit, so it requires 2 location in order to store the 16-bit register. Okay, in this example, if you look, okay, push AX, push DI, push DX, execute. Okay, the giving stack pointer location, and then the value of AX, DI, and DX. Okay, in the beginning, as we know, 1236 SS is the stack segment, and the stack pointer, the offset is 123. Sorry, 1236. This is the first. Since it's growing, it's going to be decremented. Okay, once you execute the instruction push AX, so it will decrement by 2. Now, after execute the instruction, the stack pointer is pointing at 1234. Okay, since you require to put 16-bit onto 8-bit size of the memory. And then after you execute the second instruction, push DI, it will decremented by another 2. So the stack pointer is become 1232, and so on. And the third instruction. So each time when you execute the instruction to put onto a stack, such as push, okay, after you execute the instruction, the stack pointer will be decremented by 2. Okay, for every byte of data saved onto the stack pointer is decremented once. Okay, we decremented once, and then we put another byte, decremented by 1. Since the push is saving the content of a 16-bit register, so it required to decrement twice. Okay. In the 8086, the lower byte is always stored in the memory location with a lower address. Okay, if you look here, AX, the value of AX is 24B6. B6 is the lower byte, so B6 is going to be stored in the lower byte. Okay, in here is 1, 2, 3, 3. Sorry, 1, 2, 3, 5. Okay, 1234. And then the higher byte 24 is going to be the higher location 1235, 1234, 1235. Okay. So the lower byte is always stored in the memory location with the lower address. You have to bear in mind, since the growing is by decrementing, so the upper one is going to be the lower address. Okay, so 24, the lower, the AH is saved in the location of the address 35, 1235. And AL is the higher, the higher. And AL, the lower, is 1, 2, 3, 4, the lower byte. AL, the lower, and AH, the higher. Okay, so the higher is 35, and the lower is 34. With every pop, okay, when you want to get back the data from the stack, you are going to use the pop instruction. So with every pop, the top 2 bytes of the stack are copied to the 86 CPU register specified by the instruction. Okay, and the stack pointer is incremented twice. When you pop, you want to take back, it will increment back 2 times. Okay, if you look at these examples, okay, the given stack pointer, and when you pop, okay, it's going to put back to the CX. What is the value? The value of the inside the stack. Okay, while the data actually remain in the memory, it is not accessible since the stack pointer is beyond the point. Even though when you pop, the value still remain in the register. The only thing is the stack pointer is not pointing at that particular memory. It will be incremented. Okay? So it means that even though after you uh, pop the value from the stack onto the register, the value that you pop in the stack is still remain in that stack. The only thing is the stack pointer is not pointing at that memory. Okay. The stack logical and physical stack address actually is the same as any other segment. Okay, the exact physical location of the stack depends on the value of the stack segment register and the stack pointer register. So to compute the physical address of the stack, as we know that we shift left by 1 hex the stack segment, and then we add with the offset stack pointer. In this example, if the stack segment 3500 and the stack pointer is FFFE, so calculate the physical address of the stack. Okay, if you look at the address, you shift by 1 hex of the stack pointer, and then you add with the stack segment, and then you add with the stack pointer. Okay, calculate the lower range, you add by all 0. Okay, the stack segment shift left by 1 hex, and then you plus with all 0. So this is the lower range. The higher range is you add with all f. And how you put it in the logical address, okay, by putting the stack segment and stack pointer, which in between is, okay, we continue. I think logical and physical address, I think the calculation is the same as any other code segment. Okay, can a single physical address belong to many different logical address? You can, if you look back, it should be, you look here. Okay, this is the logical address. Okay, observe the physical address value of physical address. Okay, 15020. Many possible logical address represent the single physical address. This is all the same physical address, which can be represented by uh, different logical address. Okay, if you look here, is the 1000 and the rest of it. So, an illustration of dynamic behavior of the segment and offset concept in the 1986. So, when adding the offset to the shifted segment register, result in the address beyond the maximum allowed range. Okay, because you only can have up to FFF5F. So what happen actually, it will wrap around, will occur. Okay, if you look here. Okay, what is the range of physical address if the code segment register value is FF59? So the low range can be FF590. Okay, if you add with all zero, and then if you add with sorry, the range can goes to FFFF and wrap around from 0 to 0F 58F. Okay, when you add to the highest range, if you add FF590 to all F of the offset, you can get the high range to 0F598F. You wrap up back here until here. Okay, this is the low range until FFFFF. It goes up back till 0F58F. So in calculating the physical address, it is possible that two segments can overlap. Look here, this is not a overlap segment. If you have a code segment 2500, then you have 6321. So the low range and high range is not overlapping between each other. Okay, if let's say you have the code segment of 3000, and then you have the uh, data segment is 4050, then you can have a overlapping. And the stack segment is 5000, then you can have the overlapping. Okay, now we look at the flag register. Uh, Flag register is one of the most important feature of the microprocessor, any microcontroller. I presume that you have go through it in 8051. Okay, many assembly language instruction alter the flag register bit Some instruction function differently based on the information in the flag register. There are a lot of information that you can observe in the flag register. Okay, the flag register in 8086 is 16-bit register. Sometimes we refer it as a status register. Although it has 16-bit wide, where only some of the bits are used, not all of it, and the rest is either undefined or reserved by Intel. Okay, sixth flag, called conditional flag, indicate some condition resulting after an instruction has been executed. Okay, we are going to look later on in detail. Okay, these are the six flags, which are CF carry, uh, PF is a parity, and then we have AF is auxiliary carry, ZF is a zero, SF is a sign, and then we have OF is overflow flag. The remaining three, often called the control flag, which control the operation of the instruction before they are executed. We have a direction flag, interrupt flag, and threat flag. So is an interrupt, one kind of interrupt. Okay, flag register bit used in 8086 assembly language programming with a brief explanation of each. I presume this is the same as the 8051. Carry flag set when there is a carry out from D7 and bit 8-bit operation or D15 to D16 operation. Okay. Used to detect error in the unsigned arithmetic operation. Then we have a parity flag. After certain operation, the parity flag of the result, okay, lower order byte, only 7-bit, 8-bit, lower order byte, 8-bit. If the byte has even numbers, then it will set to 1. And the parity flag is set to 1. Otherwise, it will be cleared. Even if odd, it will be cleared. And then auxiliary carry flag. Okay, if there is a carry at D3 to D4 of the operation, this bit will be set. Otherwise, it will be cleared. Okay, actually, this is used for instruction that perform BCD arithmetic. It is useful during BCD arithmetic. And then we have an interrupt enable flag. This bit is set or cleared to enable or disable only external maskable interrupt requests, which can be masked. Interrupt which can be masked. Direction flag used to control the direction of string operations. And then we have overflow flag is set when the result of a signed number operation is too large, causing the higher order bit to overflow into a signed bit. They use only to detect errors in the signed arithmetic operation. Okay, flag bit affected by the add instruction. Okay, can only have carry flag, parity flag, auxiliary carry flag, zero flag, or sign flag. In this instruction after we execute, Okay, move 38 to BH, and then you add BH with 2F. So 38 is this number 0011 10000, and then 2F, okay, 0010011111. After you add it, you're going to get it 67 in hex. Okay, where the carry flag will be 0 since there is no carry beyond D7. Okay, there will be no carry there. Auxiliary flag 1 since there is a carry from D3 to D4. Okay, D3 to D4. 1 plus 1 is going to be 0, then you have a carry at D4. And then parity flag is 0, since it is an odd number. Okay, if you look at the result, 1, 1, 2, 3, there is 5 ones. So it is an odd number. Zero flag is set. A zero flag is cleared since the result is not 0. And sign flag is 0 since D7 of the result is 0. Okay. This is one example of the carry flag being used in the add instruction. Flag bit affected by the add instruction. Okay, we have discussed this one. Okay, flag register, and add instruction. Instructions such as data transfer affect no flags. After you execute the move instruction, the data transfer instruction, there are no flag being affected. Okay, in this case, if you look, okay, you move all. Sorry, okay, if you look here in this particular, the first two instruction, there will be no flag will be affected. Okay. After the add operation, the following are the flag bits. Okay. If you look here, you add AX, BX, where the value of AX and BX in the first two instruction, then you are going to add it. So this is the result. So from this result, carry flag is 0 since there is no carry at D15. D15 there is no carry. Auxiliary flag, we look at D3 and D4 is set. Okay, we look at D3, D4. Okay, 1, 1, 1, 1, 1, then 1, 1 at D3 to D4. So it will be set. Parity flag is the lower 8 bit. So all 0 means that it is considered as even. Okay, at even, then the parity flag will be set. 0 will be not set since the result is not 0. SF will be set at D15 is 1. This is the example of the 16 bit. When you add 16 bit value. Okay, use a flag for looping. Okay, this is one of the examples. A widely used application of the flag register is to use of the 0 flag to implement in the program loops. When you want to make a loop, you put certain value and then you decrement until it becomes 0. Okay. A loop is set of instruction repeated a number of times. An example, if you want to add 5 bytes of the data, then you set the counter where it can be used to keep track of how many times of the loop needs to be repeated. Okay, if you look here, each time the addition is performed, the counter is decremented and the zero flag will be checked. When the counter becomes zero, the zero flag will be set and the loop is stopped. If you look here, CX is used as a counter. ABX here is the address offset, data address offset, and then AL is used as to store the result of the addition. If you look here at this particular instruction, jump non-zero, it will check either uh, CX becomes zero or not. Register CX is used to hold the counter. DX is the offset pointer. AL is initiated before the start of the loop. Initialized, so it becomes zero. You make it zero. In each iteration, ZF is checked by jump non-zero instruction. It will check zero flag. J and Z actually stand for jump not zero, meaning if the ZF is not equal to zero, then jump to a new location. If ZF is 1, then the jump is not performed, and the instruction below the jump will be executed. Below the jump will be executed. A jump instruction must come immediately after the instruction that decrements CX. It will check the result of the CX after being decrement. A jump not zero needs to check the effect of the decrement CX on ZF. If an instruction were placed between them, that instruction might affect the zero flag. You cannot put any other instruction between them. Okay, now we look at addressing mode. Okay, in the CPU can access operand in various ways. It is what we call the addressing mode. The number of addressing mode is determined when the microprocessor is designed and cannot be changed. Okay. In the 8086, there are 7 distinct addressing modes. Okay, we have a register, immediate, direct, register, indirect, base relative, index relative, and then base index relative. Okay, register addressing mode involve use of register to hold the data to be manipulated. Okay, register is the one that we use. Okay. Memory is not accessed. You are not using any memory location. So it is relatively going to be fast. Okay, for example, move bx dx, okay, where both of it are registered. Okay, not involved with any memory. The source and destination register must match in size. Okay, both of it based on this example is 16-bit. Coding move CLAX will give an error since the source is a 16-bit register while the destination is 8-bit. AX is 16-bit, and CL is 8-bit. Then we look at immediate addressing mode. Immediate addressing mode, as the name implies, when the instruction is assembled, the operand comes immediately after the opcode. The source operand is a constant value itself. It is what we mean by immediate addressing mode. Okay. To move information to the segment register, the data must be first to be moved to a general purpose register, then to the segment register. As you know that the segment register, you cannot move immediate data directly. It should be between the register to the segment register. Okay, in the direct addressing mode, the data is in some memory location. In the most program, the data to be processed is often in some category location outside the CPU. The address of the data in memory comes immediately after the instruction. It is what we mean by direct. The address of the operand is provided with the instruction as an offset address, only the offset address. Calculate the physical address by shifting left the DS register and adding it with the offset. Okay, note the bracket around the address. If the bracket is absent, means that it is a value that you use, 2400. Okay. If in the bracket, so it is a location. Okay, and then we have register indirect addressing mode. Okay, so if you look, anything in the bracket is considered as a it's not the value, is the location. So in here bx, the value of bx will point to the location. Actually, value of the bx is the offset. Okay, bx in the bracket. The physical address is calculated by shifting the ds by left one hex position, and then you add with the bx. This is how you find the physical address of the data. Okay, register indirect addressing actually use the same rule apply when using the register SI and DI. Source index and destination index. Register. Okay, I will stop here. I will give you all other uh, which you can go through it. Okay.